Next slide before I show you what that EVI values look like across the industry. Quick discussion on uniformity and variability. I discussed it, I mentioned it slightly previously. We understand them to mean the opposite or the converse of each other. Mathematically, though, it's not as straightforward as that. If you try and put a number on uniformity, it's a little bit difficult. So let's take the example. We've got a variability of number of 0.8. We've seen how you calculate that. So if it was the opposite, would that be minus 0.8? That doesn't make a lot of sense to me to have a negative uniformity number. So don't think we can use that one. I've seen other people have tried to subtract the variability number from 1 to give a uniformity number, and that's okay up to a point. If we had a value of 0.8, then we get a 0.2 value for uniformity. But as we've seen, variability can exceed the number 1, and we could have, for example, 1.4, and then we're back to having a negative uniformity number, which is not very appealing or intuitive. So I don't think we can use that either. The only option we've really been able to come up with is the reciprocal of variability to give us uniformity. That always produces a positive number, and it's not ideal, because as you get closer to a variability of 1, we taking the reciprocal of that, this number starts increasing exponentially almost as you get closer to uniformity, which, yeah, I'm not going to give it a smiley face. I'll give it a neutral face. It's the best option so far if you really want to express the number as uniformity rather than variability. For me, this is just a point to make that we're better off talking about variability if we want to put a number on it than uniformity. So just to almost finish us off here, probably the key chart of the whole discussion today is this one. So here we're plotting our variability number, EVI, on the horizontal axis, and the number of stages in a database that we have that's got about 1,500 stages where we calculated this variability number, and we're just counting the number of stages. There's a histogram of the number of stages within each 0.1 variability EVI band. So you can see the most frequent number we have is between 0.6 and 0.7, and we get a mean of 0.74 and a median number of 0.63. So typically we're getting, let's call it, for the sake of argument, 0.7 is a standard EVI number. And if you remember what that looks like in terms of variability of eroded area, from which we infer proppant placement, from which we infer fracture geometry, it's pretty variable. So this really is my answer to my own question on the title of this. Is limited entry giving us uniform fractures? I don't think that EVI number, whichever one of these you want to take as a typical number, is telling us that at all. It's telling me the opposite. In fact, we're getting quite variable fracture geometry, is my takeaway from that. And again, maybe just to further illustrate that, what do we consider a good number for EVI? I don't know the answer to that. Let's let's say it's the top 10% here. So the top 10%, the least variable 10% of the stages have an EVI value of less than 0.4. And that's what 0.4 looks like. And even that doesn't look particularly uniform to me. So we've a long way to go to get uniform fracture placement if you buy into this particular measure of uniformity. We can dig a little deeper if we split them up like we did previously into engineered stages compared with geometric stages. Same plot. The mean and median values for the engineered are less than the geometric. So that's, again, good news. We get more uniformity when we take the time and trouble to engineer our stages, as I think you'd hope and expect. But even then, you know, we're getting a higher proportion in this kind of good region. We're getting 15% of our stages now falling with an EVI number of less than 0.4, compared with only 7% here. So proportionally twice as many with a relatively good value for variability. And if we were to sum these up at well level, so take the average of the EVI across the stages of each well that we've looked at here, again, we get a pretty similar profile where the average well has an EVI value across all the stages where this has been calculated of around 0.7. So not particularly good in my opinion. Final thing I'm going to look at is try to see if we can detect any correlations between some of the stage design parameters that we record. For example, the number of clusters in the stage. Is there a relationship between the number of clusters in the stage and the variability? So our data here says, yes, there probably is. As we put more clusters in the stage, we introduce more variability. That one seems somewhat intuitive to me. I mean, it's not a fantastic correlation by any means. If it was a perfect correlation, this R-squared number would be 1. The number of clusters per stage would explain all the variability in the data. Here we're only explaining 15% of the variability relates to the number of clusters per stage. And that doesn't actually surprise me. You know, I think we all understand that hydraulic fracking is a very complex process, and to find one parameter that controls it is unrealistic, I think. So that's what we get for clusters per stage. If we look at stage length, again, there's a bit of a relationship there. The longer the stage length, the greater variability we have. Again, that's somewhat intuitive, I think, and or we've learnt it by other methods. Again, the correlation is pretty weak, I've got to say. And I should have mentioned here, we're only looking at engineered stages. I've eliminated the geometric stages. The geometric stages, pretty much for all the parameters, there's an even weaker correlation to the variability for them. So I'm only have time really to have a look at the engineered stages here. Next parameter is quite interesting in that, even though it's not a high number, this is the strongest correlation I'm able to show you. So the more perfs we have per cluster, the lower the variability. So that's interesting, I think. I won't try and interpret it too much, other than maybe to say a lot of these parameters we're looking at are interrelated. So we have to be careful drawing conclusions. You know, as the stage length increases, the number of clusters is probably increasing as well, and the number of perforations per cluster is probably going down. So we have actually tried to account for that. I don't have time to show you that. You can do a multiple linear regression model. That one's for another day, perhaps, where we try to understand this co-correlation between our design parameters and variability. A couple more to finish us off here. Cluster spacing. The longer our cluster spacing, the less our variability, according to our data, which again, interesting result, I think. And the final one, here we've got a straight trend line, flat trend line, basically no apparent correlation between the number of perforations per stage, the total number, and the variability. Okay. So finishing this off here, three high-level conclusions, if you like. Perforation erosion measurements, for me, have proven or shown that cluster to cluster fracture geometry is really quite variable at the moment. But the prize, we looked at that $70 billion figure that this issue causes us. If we can improve upon that, then we're going to enhance our production, and we're going to be able to optimize our well spacing. So there is a big prize available to us here. But in order to do that, first we've got to start, we've got to do more measuring, we've got to do more calculating, we've got to do more benchmarking and comparisons of this. And my final comment in here is this is some of the work that the peer consortium is going to be looking at. I've only looked at a few variables here. When we throw in other variables like all the frac treatment variables, the proppant parameters, the pumping parameters, the rates, the volumes, they, I'm sure, will have some correlation to the variability as well. And we're going to learn more as the peer consortium starts on its work. So with that, I'm sure I've overrun my time, but I will hand back to Dante to take the mic and lead us on from here.